Section 3, Unit 1, Understanding Drawings. Importance of engineering drawings. Show sizes, shapes, and features of parts to be machined. Produced in the standard format. Machining careers require ability to interpret them. Components in engineering drawings. Components include title block, revisions, history of changes, scale, and a bill of materials. The title block, A, of an engineered drawing or print contains information including part name, tolerances, and scale. The revision block, B, shows a list of changes that have been made over time. The bill of materials, C, lists raw material or components used to produce the part. Orthographic projection, showing a 3D dimensional object in 2 dimensions using different views. 3 principal views: front view, top view, and right side views. Orthographic projection uses different views to show 3-dimensional objects in 2 dimensions. The glass box shows how different views are projected or created. The front view of a drawing is projected onto the front surface of the glass box. Note the location points A, B, C, and D. The top view of the drawing is projected onto the top surface of the glass box. Note the location of points A, D, F, and G. The right side view of a drawing is projected onto the right surface of the glass box. Note the locations of C, D, E, and F. This simple isometric view shows how an object would appear in 3 dimensions. Isometric views are helpful when trying to visualize complex parts. The position of 3 principal views in orthographic projection. So you have the top on top, front, and then the right side on the right. Arrangement and identification of projected views. Compare the surface from the isometric view to those in projected views. Also, note that the back view can be positioned in any one of 3 different locations. The isometric view. So you got the top view on top, the front view on front, or the bottom left, I guess, and then the right view on the right. Some common line types and their principles. So a dark, thick line is an object or visible lines are used to show that are visible in a given view. They are thick and continuous. The number 2, hidden lines show part edges that cannot be seen in a given view. They are thin and broken into small dashes. You got 3, center lines show the center of a diameter or radius or the center of the part. Whole locations are shown where 2 center lines cross. They are thin and broken into alternating long and short dashes. 4, dimension lines have arrowheads at each end where they touch the extension lines. A dimension is listed to show feature size. They are thin and have arrowheads at their ends. 5, extension lines extend edges for dimensioning purposes. They are thin and continuous. 6, leader lines. They are angled with arrowhead at one end that touches the part feature. A dimension or note is placed at the other end of the leader. They are thin and continuous. 7, cutting plane lines are used to make an imaginary cut through an object. The arrowheads indicate the viewing direction of the section view after the cut. They are thick and have long and 2 short dashes alternately spaced. Section lines on number 8 show surfaces that have been cut in a section view, created by a cutting plane line. They are thin and angled. And number 9, phantom lines are used to show alternate positions of parts or outlines of adjacent parts. They are thin and have 1 long and 2 short dashes alternately spaced. So A over here is an object line. B right here is hidden line. C right here is a center line. D is a dimension line. E is an extension line. And F is a leader line. Dimension lines located inside extension lines with the dimension placed where the dimension line is broken. a dimension line located inside extension lines with the dimension placed outside the extension lines. Dimension lines located outside the extension lines with the dimension placed inside the extension lines. So it can go in either three of the ways. The phantom lines on this print shows the X's shown the outline of the material or stock used to make the part. So that's going to be the raw stock. A cutting plane line A cuts the part along the imaginary line. The result is a section view B with the section lines C showing surfaces exposed by the cut. Note that the ends of the cutting plane line are labeled A and that the section view named AA. So you can see the cutting plane here, and then there's the actual section view there. So these small dashed lines is the surfaces where that's actually being cut in the cutting plane. Show components. Assembly drawings show components assembled, often includes bill of materials, exploded isometric drawings, components slightly separated, center lines show direction of assembly. And there's an example of that. Continue. Basic symbols and notation. Symbols and notation keep drawings from becoming too cluttered. Diameter, radii, drill, countersink, counterbore, depth, surface finish, typical dimensions. Some standard symbols and notations use on engineering drawings. So there's a few of the symbols: counterbore, depth, countersink, diameter, radius, so forth. Basic symbols for notation. That's a surface mark. Grind all surfaces 32 micro inches max, so there's that. Finish all 32 micro inch max, and then grind all surfaces 32 degree. Alright, multiple features can be identified by a few different methods. So if you got 5 of them, you can say 5 times, or it's ½ inch between every one of them, so it's typical. Equally spaced, so that's 8 of them, and then every radius is going to be 3/16 unless otherwise specified. Allowable variation from a given size. Basic size, size show mode, total tolerance difference between upper and lower limits, bilateral tolerance, unilateral tolerance, limit tolerance, feature of size, maximum material condition versus least material condition, local, specified and unspecified tolerance, and then reference dimension. Bilateral tolerance examples. So you got a ½ inch plus or minus 2 thou. Shows that you can go above or below a ½ inch that amount. So same thing here, except you got more on the positive and you got more on the negative here. Unilateral tolerance examples is going to be all of your tolerance is going to be on one side. So 500, if you go anything less than that on this one, then you're going to scrap the part, where you got 4 thou to go over, and right the opposite on that one. Limit tolerance examples. So instead of you having a plus or minus or whatever, it's going to show you your lower limit and your upper limit on that, and vice versa on that. Cylindrical or two opposing parallel surfaces. External, shaft diameter, overall length. Internal, hole diameter, slot width. Alright, MMC/LMC. Feature must be featured of size to have a MMC and LMC. MMC is maximum material condition. External feature of size, upper limit. Internal features of size, lower limit. LMC is least material condition, and external feature size is lower limit, and internal feature size is upper limit. So pretty much you can think of this on a maximum material condition or least material, on maximum material condition if it weighs more. So if a hole is bigger, it's going to be least material condition. If it's supposed to be smaller, then it's going to be maximum material condition. Whereas on the outside of the part, if the outside dimension is bigger, it's going to be maximum material condition, and if it's smaller, it's going to be least material condition. And this shows maximum material condition will be the what I just said, the big one. Least material will be the small one. Whereas in the whole, the maximum material is going to be the small one, and the least material is going to be the big one. So whatever weighs the most is going to be maximum material. Whatever weighs the least is going to be the least material condition. A shows dimensions with specified tolerances. B shows sizes with unspecified tolerances. The tolerances block shows that the 1.875 dimension has a tolerance of plus or minus 5 thou, and that the 2.5 dimension has a tolerance of plus or minus 15 thou. So on this one, on A, it shows that your tolerance is right here, plus or minus 1 thou. For B, you actually 2.5, you'll have to come down here. It's got 2 place decimals behind, or 2 places behind the decimal, so you'll come down here to where there's 2 places behind the decimal, and it's plus or minus 15 thou. Whereas here, you got 3 places behind the decimal, so you'll look at the 3 decimal places, and it'll be plus or minus 5. Reference dimension. Anything that has parentheses around it is going to be a reference. And they usually don't have a tolerance on those in that location, but it is going to be somewhere else more than likely. So if you have 1 inch plus or minus 10 on each, or every one of these, and all of them's close to their max, we'll just say they're at their max. So 1.10 plus 1.10 plus 1.10 plus 1.10 would actually be 4.40. So that's why this is a reference dimension. Tolerances of basic sizes that add up and affect a reference dimension. 4 dimensions add up to the reference dimension. 4 tolerances accumulate. The 4 can vary by plus or minus 40 thou, what I just said. Relationship between sizes of mating parts, fits, running, and sliding, RC, locational, LC, LT, LN, and force, FN. Allowance, closest fit between mating parts. Allowance equals internal feature MMC, external feature MMC. So your positive allowance equals minimum clearance. Clearance between mating parts, hole larger than shaft, and shaft smaller than hole. Negative allowance maximum interference between mating parts, hole smaller than shaft, and shaft larger than hole. Alright, GD&T, or geometric dimension and tolerance symbols, show tolerances of form, profile, orientation, location, and runout. Datum plane from which dimensions are referenced. Feature control frame describes tolerances. So those are your different symbols that y'all need to kind of remember. Datums are identified by the filled triangles labeled A, B, C, D, and E. So A is going to be datum A. So you can see that it's got a dark triangle with a capital A in it. That's going to be a datum surface. So as you can see, everything is coming off of that datum on this thing. And B, C, and D. Neat. Parts of the feature control frame. The first compartment always contains one of the 14 geometric characteristic symbols. So on this one, you can look back and it's flatness. The second compartment always contains the tolerance information, so 0.2, the tolerance value, modifiers that describe the tolerance condition. The third, fourth, and fifth compartments, when used, always contain the datum information. So this one will be coming off of datum A. This one's in M and P. So your first one's going to be your primary, second, secondary, and third is tertiary. The flatness tolerance of the 0.2 millimeter means that every point of the surface must be within 0.2 millimeters of the tolerance zone. We're running out of time on this video, so we will continue on the next one.